Alright. Hello there, my name is Jean-Louis Bouillet. This is my Cap 1. Pathways our bodies use to produce ATP from the complete breakdown of one molecule of glucose and one molecule of fat, and how that intertwines with certain intensities and exercises within our bodies. So, as I stated, we will be using this diagram to understand the breakdown of glucose and the breakdown of fat. This source is from our textbooks, Exercise Physiology, Nutrition, Energy, and Human Performance by Mark Ardle et al. 2017. So to begin the process of the breakdown of glucose into ATP, it first goes through glycolysis. Glycolysis needs 10 enzymatic reactions in order for it to break down from glucose into pyruvate. And there's two phases to this type of glycolysis. One is the anaerobic phase, which the end product is lactate or lactic acid. And this is because NADH cannot be sustainable within the process of glycolysis. The second is aerobic, and aerobic is considered when it is able to go from pyruvate end product through the acetyl-CoA and then through the Krebs cycle. So as I stated, there are two stages. Two stages of phases. Phase one is anaerobic, which I just explained, and is considered rapid, or anaerobic glycolysis, which is considered rapid, and aerobic glycolysis, which is considered slow. Stage two is when pyruvate is changed or altered into acetyl-CoA. Um, this process this process is done through pyruvate oxidation, and from this, NADH and two carbons break off, or form NADH and two carbons break off to form acetyl-CoA, and the other carbons break off to form carbon dioxide. That From the process of pyruvate to acetyl-CoA, each acetyl-CoA enters the Krebs cycle, releasing, as I stated, two carbons and four pairs of hydrogen protons. So, in stage three, the Krebs cycle, after acetyl-CoA joins oxaloacetate, it must go through the Krebs cycle, which is a number of channels. These channels and steps include citrate, cis-acetate, isocitrate, oxalosuccinate, ketoglutarate, succinyl-CoA, succinate, fumarate, malate, back into oxaloacetate again. And since in glycolysis two pyruvate molecules are created, it must go through each one must go through the Krebs cycle. So from the Krebs cycle, it produces NADH, and one NADH is equivalent to 3 ATP. So since 3 NADH are in the Krebs cycle, therefore 9 ATPs are produced. And since FADH is only produced once, and FADH only produces 2 ATP, there's only 2 ATP from that. Next is GTP. GTP only produces 1 ATP, and there's only 1 GTP in the production cycle. So since the Krebs cycle, in one Krebs cycle, there are 9 ATPs produced, but since it has to happen twice, 18 ATPs are produced. The next step is oxidative phosphorylation. This is known as electron transport chain. This is when reduced coenzyme complexes become oxidized and further the production of ATP. And by this, I mean electrons are being transported and lost, as well as oxygen is being reduced. In this process, the compounds go through a protein gradient, and within this protein gradient, hydrogen protons are being released within are being released to keep stored energy and to produce that stored energy into ATP. It goes through kind of what they call a matrix within that system. It does this by going through ATP synthase, which goes across the membrane, as I just said, which allows that hydrogen protons to be transferred into ATP energy, or into ATP, sorry. So, the total ATP from one molecule of glucose is a total of 32 ATP. So as I stated, I'll break it down a little bit further. Since a total of 10 NADH molecules are produced leading into the electron transport chain, this is from two in glycolysis, 2 in the process of pyruvate to acetyl-CoA, and 6 in the Krebs cycle. And for every 1 NADH, there are 3 ATPs produced. So there are 32 ATPs, but 5 ATPs are used as energy transport ATP across membranes, but another 3 are gained from the FAD molecules from electron transport. And so lastly, the substrate level phosphorylation, which involves GTP. GTP adds another 2 molecules, making it a total of 32 ATPs yielded from glucose. So for 1 molecule of fat into energy, or ATP, these are the diagrams we will be using. So stage 1 is the breakdown of triglycerides into glycerol and free fatty acids. Stage 2 is the transport of free fatty acids into the blood. Stage 3 is uptake of the free fatty acids in the blood. Stage 4 is to prepare the free fatty acids for catabolism, which is breaking it down. Stage 5 is activated fatty acids when entering muscle mitochondria. Excuse me. Stage 6 is the breakdown of fatty acid into acetyl-CoA by beta oxidation, which then produces NADH as well as FADH2. This causes the splitting of carbons, which then joins the coenzymes. And then beta oxidation continues to happen until the full breakdown of that fatty acid into acetyl-CoA, which stage 7, it is entered into the Krebs cycle and the electron transport chain. So, as I stated, triglycerides are first broken down into glycerol, and glycerol is equivalent to 9 ATP. But before that, glycerol has to go through glycolysis by being accepted as 3-phosphoglyceraldehyde, which then goes to the pyruvate system through substrate phosphorylation to form the ATP. And in this process, hydrogen proton atoms pass on to NADH plus and then go through the Krebs cycle and pyruvate. And from the breakdown of 1 glycerol, it is equivalent to 19 ATP, as I stated earlier. But among that glycerol comes with the 3 free fatty acids. Each fat molecule has 147 molecules of ADP, which are then transferred into ATP through beta oxidation, and the coenzymes joining the splitting of carbons to create that ATP. And in total, 441 ATP molecules are formed, along with the 19, to have a total, and our diagram says, of 460 ATP. So how these pathways interact across exercise intensity and duration? Well, when considering glucose and its pathway, it doesn't necessarily need oxygen, as we stated, because it can go through the phase 1 process, which is the rapid glycolysis process, which allows your body to use glucose as a quick energy source for either rapid exercise movements such as high intensity, or it can go through aerobic phase and be used during light and moderate exercise to withstand those workouts and those certain exercise demands. On the other hand, when considering fat, its pathway is slow and needs oxygen. It takes longer to break down. So this system is used during prolonged exercise because of its slow breakdown. But it also since it also has a lot of energy within fat, it also is being used when your body has no more glycogen stores. So limiting factors in ATP production. From glycolysis, the limiting factor is NAD. When it is unavailable, the other half of glycolysis is slow or shuts down, as well as it has been known According to the text, that oxygen has been an inhibitor to glycolysis. In oxidative phosphorylation, lack of oxygen is also a limiting factor as well. And for beta oxidation, oxygen is another limiting factor. For beta oxidation, it is required to have oxygen in order for it to complete its process. So in conclusion, based on the pathways and the energy provided from either glucose or fat, this applies to the real world by informing that our bodies use certain systems based on the selected type of demand our body recognizes throughout our central nervous system. And in response to that, it selects whether to use the fueling system of glucose because of either a rapid movement or a light or moderate exercise, or our glycogen stores have been depleted, which makes our bodies use fats as a fuel source because of its stored energy and amounts of high ATP amount. Thank you for watching, and goodbye.